Morning, guys. Happy Friday. Last day of our first week of trying this stuff. Today, we're going to be talking about the Henderson-Hasselbalch equation, which is related to buffers. So yesterday I introduced what buffers were, and we'll have a little review of that obviously today. And then we'll walk through some math using this equation, and this equation is going to make our lives much easier than trying to do the ice table, mine table stuff that we ended up doing yesterday. So I think you'll like today's lesson a little better than yesterday. The one thing I do need you to do before the end of the day today, and I think I have it closing at like 4 o'clock today, so ideally you're getting this done by 4 p.m. today, is that quick little digital check-in that I had posted on It's Learning. It's 3 questions. It's super simple. If you've talked to anyone else, or if you've texted anyone else, or if you're in the group chat, it's I don't even care what you get on it. In reality, I need you to do it to make sure. Again, it's more of an attendance check than it is anything else. Once spring break is over, obviously today's the last day for a whole week. But once spring break is over, we'll jump back into acid-base stuff. We are pretty close to the end of this unit, so my plan is to have a couple days of review. Probably, I'll give you guys the review packets like usual, and then we'll see what a take-home test looks like. And again, yeah, it's the times we live in, so I'm sure that'll be a much more enjoyable experience than having to take your test with me in the room and a fan in the background acting like it's canceling out some noise. Anyway, so let's jump through the Henderson-Hasselbalch equation. Today should be shorter than yesterday. We should definitely be able to keep it under a half hour. So, buffer review. What 2 things do you need to make a buffered solution? So the 2 things you need are going to be a weak acid and its conjugate base. And more often than not, when we're talking about buffers, that's what we're talking about. We are using weak acids for buffers almost always. But you can also make a buffer with a weak base and its conjugate acid. Okay? Either of those is what you need. Again, you cannot use something strong. I mentioned this yesterday, but you can't use a strong acid or a strong base to make a buffer. It doesn't work. It absolutely must be a weak acid or a weak base. Well, what purpose do buffers serve? Buffers are solutions that resist pH change. All right, so they resist a change in pH. Well, why is that useful, right? So it's useful because I can use the example of like household products, all right, or even food products, beverages, right? Like any type of juice or drink that we drink is almost always buffered. And the idea there is there's a certain pH where a food product is going to be optimal or to have the best flavor or taste the best or preserve itself. So oftentimes a lot of beverages are buffered, and in the medical industry they use buffers. For example, prior to surgery, they usually have people drink a buffered solution to control the stomach acid as the person is going under for anesthesia. So there's many purposes for buffers, and again, they're what they do or what their purpose is chemically is always going to be the same. It's just to resist that change in pH in some way, shape, or form. So again, it can be used in household products, food products, medical industry, and it's just some situation where a pH change needs to be minimized. What are some pairs that could work to make a buffer? So, I mean, honestly, like I haven't really made you do a ton. You've kind of just been sitting here listening to me for a while. So if you want, you can pause it and try to think of some ideas that could make a buffer. Again, what you want is a weak acid and its conjugate or a weak base and its conjugate. So go ahead and pause it. In theory, you paused it, but we'll see if that actually happened. Maybe you just waited for me to start talking again, just like in real class. Feels like home. But here are some examples, okay? So I could use HCN, which is hydrocyanic acid, and of course CN1 minus, right? That's its conjugate base. I could use I'm still in subscript or superscript rather. HC2, H3, O2, which is acetic acid, and its conjugate, which would be C2, H3, O2. That's 1 minus as well. Okay, those are some acid examples. We could do base examples. Um, sorry, trying to get comfortable. If I had ammonia, NH3, and its conjugate acid, which is ammonium. Okay, that would totally work. Let's see. We could get one of those weird nitrogenous bases in, right? I could have like methylamine, which is CH3, oops, NH2, and then its conjugate acid would be, oh my gosh, I need to calibrate the smartboard. CH3, NH, okay, yep, mm-hmm. 3, 1 plus. So you get the idea. It doesn't really matter. Again, you could make a buffer with all sorts of crazy different weak acids and weak bases. But what does matter is that you have a weak substance and its conjugate in the solution at the same time. That's what's going to produce a buffer. All right, so let's go to the next slide. If you have equal concentrations of weak acid and its conjugate, how are the pH and the pKa related? Now, this, as my hint is going to give away entirely, is at the halfway point of a titration. Okay, if your weak acid, which we'll just use HA, and its conjugate, we'll use A1 minus, are equal to one another, you're at the halfway point of a titration. And when these two compounds are equal with one another, we know that pH and pKa are the exact same. All right, so this relationship of pKa and pH being the exact same at the halfway point has shown up time and time again, and it absolutely will show up on the AP test. More often than not, they like to give you a titration curve, like I showed you last week Thursday, I think it was, whenever I started looking at titration curves and talking about the halfway point for the first time. But this relationship is going to show up on the AP test. It absolutely will. They love to use this halfway point HA, A1 minus, or weak acid conjugate base relationship, pH equals pKa relationship. It's a big deal in this topic. All right, so now let's introduce the Henderson-Hasselbalch equation finally. If I have a buffered solution, more often than not, there won't be equal concentrations of the two conjugate acid-based species. So yesterday we started our sheet with an equal molarity of acetic acid and sodium acetate. And then we switched and we went to 2 different molarities after we had neutralized some of it with some base. But again, in general, what we're going to have here is buffers that don't have equal molarity of conjugate base and weak acid. Okay, so we have an equation. This is called the Henderson-Hasselbalch equation. Sometimes it gets just shortened as HH equation to make life a little easier. But this is what it looks like, and this is in your formula packet. And this is only used for buffers. All right, you should really write that down because people get into trouble when they try to use this for something else. So this is the Henderson-Hasselbalch equation again, and it's a buffer equation. Only for buffers can we use this thing. So if I make a buffer with equal concentrations of weak acid and conjugate base, what is the fraction, this fraction right here, of A over HA equal? Well, if they're equal concentrations, right? If this is 5 and that's 5, well, this fraction then equals 1. If this is 2 and that's 2, then this equals 1. Okay, you get the idea here. So this equals 1.00. Oh, it's going to make it ugly. Okay, hold on. We'll just do this. There we go. And then my next question to you is, well, if this fraction equals 1 when these two concentrations are equal, what's the log of 1? You can punch that in your calculator, but spoiler alert, it's nothing. So in other words, if you create a buffer with equal molarities of conjugate base and weak acid, or weak base and conjugate acid, either which way, the pH of your buffer is going to equal the pKa, whatever that might be. I don't know why I keep typing in 1, whatever. All right? And this equation gives us that exact same relationship that we just had on the previous slide, right? The previous slide was saying, hey, if these two things are equal, what's true about this? Because it's the halfway point. Well, pH equals pKa. Well, using the Henderson-Hasselbalch equation, we actually end up with the exact same relationship. We can just plug in real numbers to prove it, right? So if this was the same, if this molarity is the same as that molarity, the log of 1 is 0. And then what you're left with is this whole factor just goes away, and pH equals pKa. So there you go. All right, so let's try a real example here. Sort of real. Same exact concept right here, though. But so if I create a buffer with 0.5 molar acetic acid and 0.5 molar sodium acetate, this is the exact same one from yesterday. All right, let's calculate the pH using the Henderson-Hasselbalch equation instead of using an ice table like we did yesterday, which was a giant pain. So I have a Ka of my weak acid, and we're going to need that. We need that Ka value because we need to solve for pKa. And remember, in your formula packet, that pKa equals the negative log of Ka. So all we need to do is if we take the negative log of this 1.8 times 10 to the negative fifth, I'll scooch that over. There we go. All right, we're going to get pKa. So pKa is going to equal 4.74. 4.745, I think it was. I have to grab my calculator. I'm going to pause it and grab it. All right, yeah, I'm back. Yep, and it's 4.745. We are good. So we can plug that in, all right, and we have molarities now for each the weak acid and the conjugate base. Again, so this is the one weird thing with buffers and really one of the things that screws people up. But we have this molarity of sodium acetate. Okay, and this is actually salt, right? Sodium acetate is NaC2H3O2, and it's a salt compound. But the sodium is irrelevant, right? That is literally just going to be a spectator ion. So what we really, really care about here is that acetate. Now, since this is a salt, it's going to dissociate. It's aqueous. We have a molarity for it, so it's going to dissociate 100%. So we actually have 0.5 molar sodium ions and 0.5 molar acetate ions. So when I'm asking for the conjugate base, right, the A1 minus, the conjugate base of my buffer, what I'm really looking for in this example is the acetate, which is 0.5 molar. So I can plug all this in, right? So I can plug in, my pKa is 4.745. And my log, let me just move this out of the way. Maybe. Oh no. There we go. And my log is going to be 0.5 divided by 0.5. And again, you can leave these as they are, right? I mean, if you recognize this is obviously going to be a fraction of 1, which it is, okay, the log of 1 is going to be 0, then we know our pH is just going to equal 4.745. But for the sake of argument, you're more than welcome to plug it in, right? So if I take 4.745 plus the log of 0.5 divided by 0.5, hey, it's the same number. Okay, so pH is exactly what we got yesterday. After all the ice table craziness, we ended up with the exact same answer. But the Henderson-Hasselbalch equation just makes life much easier, right? And it saves us a ton of time. And especially if we recognize this, right? If you recognize this and get familiar and comfortable with realizing when the pKa and pH are going to be the same, you don't even really have to set this up. You can just realize, oh, okay, that's the same molarity as this molarity. Acid and base have the same concentrations, so pH just must equal pKa, and you could have just done this over here, and you would have been good. So let's change it up a smidge, right? To create buffers with different pH values, you could use a different concentration of weak acid. So this is talking about like a laboratory setting. If you're actually in a lab, right, what you do to make a buffer is typically you take solution of weak acid, okay, whatever molarity you want or whatever molarity you have, and then you literally add solid salt, right? So you're taking like scoops of solid salt to add into your weak acid. Now that salt, of course, needs to contain your conjugate base, but you're going to add salt until you achieve the desired pH. All right, so that's typically how buffers are made. There's other ways to make buffers. One of the other common ways to make a buffer is to start with a weak acid and then just neutralize some of it, because we know that as you neutralize a weak acid, you actually produce its conjugate. So if I have a lot of weak acid, a very strong, very concentrated solution of weak acid, and I add some strong base to that, I would neutralize my weak acid to produce conjugate base. So when you neutralize that weak acid all by itself, you actually do produce a buffer as well. It's usually not as good of a buffer because you need a lot. You need a high concentration of both weak acid and conjugate to make a good buffer. But it works. It's technically a buffer. So anyway, so to make a 750 milliliter a buffer solution with a pH of 5.14, you will need to add a certain mass of soluble sodium acetate. The acetate concentration would be A1 minus in our formula. So let's solve for A1 minus using the exact same 0.5 molar acetic acid solution. So the end goal here is a buffer with a pH of 5.14. So we want that. We know that in our formula. The pKa of my weak acid is still the exact same. We're still using the exact same stuff. We're just messing with the pH a little bit. So I have 5.14 for my pH. I have 4.745. I don't know why. For my pKa, I have 0.5 for my molarity of acid. Okay. And what I don't know is the molarity of my conjugate base. That's what I'd like to solve for first in this problem. So the algebra here is a little funky, right? We have this log and we have our value of x inside that log, so we'll need to eventually unlog that, so to speak. But I can start doing some simple algebra. I can take the 5.14 and I can subtract off the 4.745. So let me do that. And I'm getting 0.395. All right, and I'll write this down just to make sure we have an intermediate step here. 0.395. And that's going to equal the log of, let's see if I can just copy and paste that here. The log of A1 minus over 0.5. So now we want to isolate that value of x, right? So now we're going to get rid of the log. It's a positive log, so unlike the pH equation, right? In our pH equation, we've been taking 10 to the negative pH to solve for H1 plus. But in this case, it's a positive log, so we're actually going to take 10 to the positive 0.395. So I can do that. So 10 to the answer. And I'm getting 2.483. Again, there's other digits. I'm not going to round that officially until the very end. So 10 point, I'm sorry, 10, not 10, 2.483. And that's going to equal my concentration of base over my 0.5 for the acid, which I know. So all now I need to do is multiply by 0.5, and I should be good. And I get a final molarity of my base equal to, sorry for all the jumping around here, and this is going to equal 1.24. And this is a molarity, so we'll drop a big M after it. And that's half of this problem. I've kind of broken it in two. Okay, so again, here was the goal, right? The goal was, let's make 750 milliliters of a buffer with a pH of 5.14. So if we're using the same stuff, acetic acid and sodium acetate, I have 0.5 molar acetic acid. We plug that into the expression, and we solve for what molarity of salt we actually need. Now that we know the molarity of our salt, we can finish and do some factor label math to solve for the grams of salt that we need to add. So, prediction, if our buffer with equal concentrations has a pH of 4.74, sorry, and we want a buffer of 5.14, which relationship below should be true for our new buffer? Should we have equal acid-base? Should we have more acid than base? Or should we have more base than acid? Well, if when they were equal, it's 4.74, when we're more basic than that, meaning the number has gotten bigger, we absolutely should have more base than acid, right? This is just kind of something to think about, a thought process of how we approach, these problems. And it's a place you can catch yourself too, really, in reality, because we realize our pH should be bigger than what it is when they're equal. Okay, well, if that's the case, we must have more base at that instant, right? And the base must be in larger concentration if we have adjusted the pH upward. If I adjusted the pH downward, let's say I wanted a pH of 4.14. Well, in that case, now my acid must have been in greater concentration than the base. Because again, when they're equal, pH equals pKa. And if they're not equal, and it's bigger, the pH is larger, we have more base. If the pH is smaller than the pKa, then we have more acid. All right, so here's where we are with, I'm going to need my, so let's finish this problem then. Okay, so now let's calculate the grams of sodium acetate we need to add to our 750 milliliters of 5.5 molar acetic acid to create this buffer. Now we're going to solve for grams. So I have this volume. We solve for the molarity of my base, right? We know that the molarity of the base is 1 liter on the bottom. Okay. And the molarity we got was 1.24 molar. And this is of what? This is of sodium acetate, right? That's salt. Now, the acetate's what we care about. The acetate is the ion we want in solution. But in order to get that acetate in our solution, we have to add sodium acetate, that whole compound. I can't just go into the back chemical storeroom and grab a bottle of acetate. It doesn't exist. Acetate needs to be with something else. It needs to be combined with something else. It's not stable as a lone ion in the solid form. In an aqueous form, it's absolutely stable as a lone ion. But that's not how chemicals are sold. So we have to grab the solid sodium acetate. So we have liters, we have moles. Now we just need to convert moles into grams. So we need the molar mass of sodium acetate. And I need to go grab my periodic table. I'm not prepared today. All right, so the molar mass is 82.034. And here's our setup. We have 750 milliliters or 0.75 liters of the buffer that we want to produce. We figured out that our molarity of the conjugate base from the Henderson-Hasselbalch equation must be 0.124 molar. Or sorry, 1.24 molar. Let's try that. And we know the molar mass of the salt that contains the conjugate base. So if I punch all this in, 0.75 multiplied by 1.24 multiplied by 82.034, I'm getting 76.3 grams that we need to add, which is quite a bit. And that's 76.3 grams of sodium acetate. So that's NaC2H3O2, or as it's more affectionately known, nacho. And there we go. So this is an example of how a buffer problem could look. Okay, our buffer, we wanted a pH of 5.14. We have a pKa of 4.74. So our buffer must need more base than it does acid. We used the Henderson-Hasselbalch equation to figure out the molarity of base we would require to make this buffer. We then used factor label math with that molarity to determine how many grams of salt would need to be added. I've got one more of those coming up. Let's do a couple precursor problems here just to get us on the right foot. So I have 1 liter of buffer made from 1 molar nitrous acid, which is weak. This isn't NO3, it's NO2, so this is a weak acid. And the conjugate base is going to be introduced using sodium nitrite. Again, good choice, because we want salt that contains our conjugate, which is NO2 1-. But that cation of our salt must be something that's neutral. Sodium is always a good choice because sodium is a neutral ion. So we have 1 molar of each of these two substances. What's the pH of this buffer? Well, we could use Henderson-Hasselbalch, right? So pH equals pKa plus the log of base over acid. So A1- divided by HA. I'm not even going to put a little fraction bar in because it's not worth my time. All right. So if these molarities are the same, 1 and 1, which they are, all we need is the pKa, right? pKa and pH are going to be the same because this whole factor, when this ratio is 1, is going to be 0. Log of 1 is nothing. So let's just take the negative log of our 4.0 times 10 to the negative 4. And I'm getting a pH of 3.4. Suppose let me use all the sig figs here. 3.398. How about that? right? That's pKa, but it's also pH, right? Because, again, when these molarities are the same, pH and pKa are the exact same thing. If I add hydrochloric acid to this buffer, show the reaction that would take place. All right, so this is like showing what buffers do, right? We're adding strong acid. So strong acid is H1 plus. Again, the Cl, the chloride from our HCl, is still technically in solution, but again, it's kind of irrelevant because the strong acid, all we care about is the H1 plus. So I add acid to my buffer. What inside my buffer will neutralize that acid? Well, it's going to be the base, right? What's the base of my buffer? The base of my buffer is the conjugate base right here, NO2 1 minus. Oh, no, it's not going to let me type there. There we go. All right. And when these two things react, I'm not even going to put an arrow here because it's, again, just not worth my time. There'd be an arrow in the middle there, obviously. But we're just going to combine those two. So the acid will donate and the base will accept, and we're going to get our weak acid right back out. On the other side, right, let's say I added some sodium hydroxide to my buffer. Well, sodium hydroxide is a strong base. And again, we don't care about the sodium, it's a spectator. I'm going to react this with HNO2, which is the acid of my buffer. When these two things react, I'm going to get water. And I'm going to get NO2 1 minus, which is the conjugate base. So whenever you add acid to buffer, it gets neutralized by the base and produces the conjugate acid. Whenever you add base to a buffer, it gets neutralized by the weak acid and produces conjugate base, kind of like we looked at yesterday. But just wanted to revisit that and show that one more time. Again, there's obviously arrows in here, and they would just be forward arrows because this isn't reversible. This is an acid-base neutralization. So this will react and react and react until something runs out. All right. One more problem. Let's try to get through this quickly so I can stay under a half hour. I don't know if that's possible. Sorry, guys. Thought it'd be shorter. But let's use that same molarity of nitrous acid, 1 molar, and we're asking how many grams of sodium nitrate do I need to add in order to produce a buffer, or 500 milliliters of a buffer with 3.60 for a pH. We're going to use the Henderson-Hasselbalch equation right here, and let's set that up. So my pKa from the previous problem was 3.398. My molarity of acid is given to us. We know the acid has a molarity of 1. And my molarity of base is something that we would need to figure out. Again, we've shifted the pH, right? We don't have this pH when these two molarities are the same. We have a pH that we want it to be higher, right? And in reality, I suppose I should plug that in. Oops. There we go. I'm going to try to shift this whole thing over here so we can actually see it. Let's go like this. There we go. And we need to do some algebra to solve for our concentration of the conjugate base. Again, when we solve for this concentration, we're technically solving for the nitrite. But in reality, in order to add nitrite into our buffer, we must use salt. Okay, because nitrite doesn't exist all by itself. We need to use some sort of salt that contains the nitrite. So let's do the math. I'm going to take 3.6 minus 3.398. I get 2.02, or 0.202. I need to unlog that thing, right? So kind of like we did in the previous example, I need to take 10 to the power of both sides to get rid of the log. So if I take 10 to the power of 0.202, I'm getting 1.59, and again, there's more digits behind that, and that's going to equal this ratio. And now I just multiply by 1, which does a whole heck of a lot of nothing, and I get a final molarity of my conjugate base equal to 1.59. All right, that's half the battle. We know the molarity. I'm going to put a big M after that, actually, just to make sure. Okay, we know the molarity of the conjugate base that we need in order to reach this pH for our buffer. Now, we need factor label math. So I've already kind of preemptively set it up just to make sure I don't have to go running for anything again. But my molarity of the conjugate base is this. I'm making not 1 liter. Oops. We are making 500 milliliters, which is 0.5 liters. Okay. And we are going to use this molarity of our conjugate. So I have 1 liter on the bottom, and I have 1.59 molar or moles on top. The molar mass of sodium nitrite is 69.00. So we will take and multiply by the molar mass. And if I punch all that in, 0.5 multiplied by 1.59 multiplied by 69.00 equals 54.8.9. Let's try that. 54.9 grams of, sorry, let me finish it here, NaNO2. And that's our final answer. I'll just leave it down here, I guess. But that's it for today. So thank you for hanging with me. I know I went a little long once more. Happy spring break. Enjoy your time off. Don't worry too much about chemistry over the next week. We'll pick it up when life resumes in 7 days or 9 days, something like that. It is my birthday, so happy birthday to me as I sit here and self-quarantine with my crazy children. I hope everyone's healthy. I hope everyone's happy, and we'll talk to you guys shortly. Thanks.